real quick here. So this is meant to represent space travel at high speeds. Is there a limit to how fast a spacecraft can go? What do you think? What do you think?
If nothing else, you have to consider the fact that at a certain speed, the spacecraft will demolish itself. And you also have to abide by the speed limit of the universe.
Which is what?
The speed of light.
Okay. Yeah, the demolish itself part I'm not on board with. Because you could travel at arbitrarily high speeds up until speed of light. I'll buy that though. Yeah, there is a limit here. And this is a limit in a mathematical sense. And we'll kind of get back to this in a little bit. We'll be able to take this limit and show why it is that spacecraft can't exceed the speed of light. There's a reason. There's a reason, and we'll get to that. But first, we got to delve through some limits. Now, I'm going to make this pretty quick because you guys had a chance to already look at this stuff a little bit. This is, okay, we're going to come back to this. This is why. This is the why you can't ever travel, well, you can't even travel the speed of light. Why that is the limit you can approach, but you can never get there. Okay, so we'll come back to this, to that very page. Okay, but let's talk about the concept of a limit real quick. So remember now, you guys have probably gone through this stuff at various times during the summer, so I'm going to touch base on all of it. But again, just maybe go through it a little faster than I otherwise would have. So if we've got some function here, f of x is equal to the quantity x cubed minus 1 divided by the quantity x minus 1. Okay. Are there any values for which this function is undefined? 1. How come? You can't divide by 0, right? So we know that 1 is going to have to be excluded from the domain of that function. That's one thing we could say right away. X cannot equal 1. What is f of 3? What's that going to be? What is it? 13 is right. If I evaluate this at 3, how'd you get that? You're going to get 3 cubed, so 27 minus 1, that's a 7. 27 minus 1 over 3 minus 1, that's 26 over 2, which is 13, right? So that's the answer, okay? This function is defined at x equals 3. Okay, now I forgot. Let me just look ahead real quick here. So, yeah, how about this one? We already said the function's undefined at 1, so the answer would be undefined. There is no, you can't evaluate that function at 1, okay? But could you take limits, right? Like, for example, what if I'm going to go back just a little bit here. What if I wanted to take the limit of this function as x approaches 3? Oh, yeah, you betcha. Go. I unplugged that one in the back. I already unplugged it. I just want to make sure something wasn't going on, that maybe the charger was bad or something. So you'll see it's the one that's unplugged. What is the limit of this function as x approaches 3? And why? Based on what you looked at this summer. Let's talk about this. What's the limit of this function, f of x, as x approaches 3? What is it? 13 is the answer. Okay, we'll come back to that. How about this one? Does the limit exist to this one? Could I take the limit of that function as x approaches 1? I can. How come I can take a limit even though the function is undefined? Why is that limit 13? What is the meaning of a limit? Can you guys just kind of summarize that for me based on the stuff we talked, or you guys looked at? What do you think?
The limit would be how close, basically getting right how close to it without touching it.
Okay, yeah, so the limit of a function is the value that the function is approaching as x approaches a certain specific value, right? So in this case, we're taking a limit. That's supposed to be an arrow. God, I got to do a better job of like making this a little bit neater. Whoops. When we use this kind of notation, and we'll get into this in more detail, You saw that a bunch this summer, right? That says the limit of the function f of x as x approaches 3. The really key thing about a limit is it is not at all concerned about what actually happens at 3, because in the limit you never get there. You just approach closely. So as x approaches a value close to 3, what value is the function approaching? We know the answer is 13 because you already told me on a previous slide back here. Oops, where was it? I guess it was right there. You told me that the value of the function at 3 is 13. So that's the point that we're approaching as x approaches 3. As far as the limit's concerned, though, it's irrelevant that the value of the function is 13 because you never get there. But that's the value you think you're going to be approaching for the function. Does that make sense? So in the limit, you never get to your destination. You just get arbitrarily close. Okay? So what about a situation like this guy? Okay? The limit of f as x approaches 1 is equal to 3. But why? You would never know that. You could figure it out, but why? I'm telling you that's the answer. Can anybody defend maybe how they could show that that's the answer? What do you think?
Well, maybe you could factor the x cubed minus 1, and then because if you plug in 1 with direct substitution, you have it in, I think, indeterminate form, so you can maybe go from that.
You do, right. Okay, so now, I don't know if we'll get to all this stuff today, but if you try to evaluate, how familiar are you with the concept of direct substitution or direct evaluation from this summer? Is that ringing a bell? Be honest with me. 5 meaning very familiar, 1 meaning very unfamiliar. How familiar are you? Okay, so I'm seeing some 1s and 2s. There's some high numbers, but so we're going to talk about this. We can't evaluate this thing directly and get an answer because we get a 0 on the bottom, right? That makes sense? So we got to use some other method. Now today we're not going to get up to the point where we talk about how do we use analytical techniques to find the value of the limit. We're just going to look at some non-analytical techniques. How could we use maybe a numerical table or a graph to come to this answer? What would happen if I were to graph this function to you, suppose? What do you think is going to happen as x approaches 1 if I look at a graph of this function? What do you think is going to happen?
Could it possibly turn away?
Well, what y value would the graph appear to be approaching? 3, guaranteed, absolutely guaranteed, and we'll look at that. Okay, so if we go back, I think I've got right here. Got these all built. So if we look at this function, here it is. Here is the function, right? X cubed minus 1 over x minus 1. There's its graph, okay? So look, if I drag a point along this function, it's giving me a bunch of ordered pairs that sit on that function. What do you think is going to happen when I get to 3? Well, where's 3? Oh, not quite. Oh, it's 1, sorry. It was 1, not 3. Whoops. What's going to happen when I get to 1? It may not, and unfortunately, oh, there it is. I got it. Look what it does. Notice what kind of point does it give me? Open point. Look, all these other points are closed points. Those are points that exist on the function, but when I get to 1, it gives me an open point, meaning it doesn't exist, right? If it's open, it's not part of the function, and the output is undefined. I could go up here and I can do f of any value I want, 1.1, and it gives me an output, but if I make that f of 1, it tells me it's undefined, okay? So the graph is very helpful here. Notice, though, that with technology, when you graph something, what's the weakness of graphing this function with technology when you look at that graph? Like, what would be a better, like if I were to graph this by hand, I could do a much better job Because what would I include? I would include a hole in the function at x equals 1, right? There would be one little gap, which I would represent with an open point that represents that one infinitesimal point that is excluded from this graph, right? But everything else looks good. So that's the one weakness. When you look at a graphing technology, graphing a function, usually the important points, the holes, the places where the function doesn't exist are disguised, right? They just don't show up. But it's there if we look for it. But you can see that as this function approaches x equals 1, it's pretty clear from the graph that we're approaching a y value of 3, isn't it? Everybody agree? Okay. We could do this with a table. Okay, if I make a table on Desmos, I'll show you how to do this. It's kind of a slick little trick. So I'm going to graph the function, and then if I go up here and I click the gear, I can hit Create Table. And it builds a table of values from that function. There's the inputs, there are the outputs, right? What do you think?
Some of the power strips aren't turning on the inside, so I'm going to be back in a little bit with help.
Oh, perfect. That works. Okay, awesome. Thank you. Okay, so then I can build this table as big as I want to. Notice it's showing the points that are graphed on here. You can do some slick little shortcuts with this, like if I wanted to, for example, let's say we're going to start at 0. Oops, I could start at 0, and I could increase by 1/10, for example. Okay, and then if I keep hitting return, it's just going to add points every 1/10, and it graphs those on the screen. And I can even include, if I want to, I think, well, no, I can't. I guess it won't let me put the ordered pairs in there, which is fine. Right? So it's easy to build tables from functions in Desmos. And if I look at all those values, if we look at the missing value here, you can kind of extrapolate or interpolate and make a pretty good guess what value you're approaching. It would work even better if I pick values that were closer together, right? Like what if I pick values, like let's say I'm going to go from 0.990 down to 0.991. That's going to even do a better job. As I get to 1, you can see that as I'm approaching 1 from values of x less than 1, the numbers are building towards what looks like 3. And as I approach x equals 1 from decimals greater than 1, it looks like the numbers are receding back to 3. Agreed? And so either way you look at it, both the table and the graph make a prediction that when we get to 1, we would anticipate having a y value of 3, even though the function's undefined there. The limit doesn't care about that. The limit just wants to know what the trend is, right? Make sense? Okay? Give me 1 to 5 so far on that concept. That makes sense? Okay? All right, so then if we want to kind of describe the flavor of limits, here's one way I like to do it. Okay? How to imagine this. Imagine microscopic two-dimensional ants that live on functions on my Promethean board, right? These ants are blind, but they have developed the ability to sense their position in the xy plane with perfect accuracy, right? So the limit of a function as x approaches the value c corresponds to the y value that these ants anticipate stepping on when they get to x equals c. Where would they think they're going to be, even though they may not be there, right? That's irrelevant. Where do they anticipate being when they step on that point, okay? And from either direction, from the left, from values less than c, or from the right, values greater than c. That's a good way to think about limits, okay? And that's how we write it. The limit of f of x as x approaches c equals L, where the number L is the value, the y value they think they're going to step on. Okay, so let's begin our exploration of limits by taking a look at some graphs of functions. So what if we look at, we already looked at one like this, f of x squared minus 4 over x minus 2. Okay, if we want to take the limit of that function as x approaches 2, we're going to look at the behavior in and around the value 2. Well, what's the graph predict we're going to get? Yeah, it looks like 1, 2, well, what's it going to be? 4, right? Everybody agree? So this picture here is telling us that the limit of f of x as x approaches 2 is equal to 4. How come? Because the coordinates of the point that the ant anticipates stepping on are 2, 4. Okay? Does the ant actually end up at y equals 4 when he steps there? No, because the function's undefined. He just blinks out of existence, I guess. I don't know. It falls into some kind of alternate universe maybe, but who knows? But we won't go there, right? But that's, you see the idea. We don't care what happens when he actually gets there. The limit is just where does he think he's going to be. Okay, what about this guy? What about g of x, which is the absolute value of x minus 2 divided by x minus 2? What do you think's going on there? Look at this graph. What do you think the limit of this function is as x approaches 2? Ah, okay, that's a problem. Depends on what side, and therefore there can't be a preferred direction, right? The universe is isotropic. This two-dimensional mathematical universe is isotropic. It shouldn't make any difference what direction you approach things from. All directions should be treated equally, so there's a problem. Approaching from the left and the right gives us different answers. That's a red flag. That's telling us that the limit of, this is g of x, limit of g of x as x approaches 2 is undefined, doesn't exist. Okay? Well, we'd say the limit, really what we would say, we would just do this. We would say dne does not exist. Okay? Because there is no specific place that an ant walking from both sides would anticipate stepping on. How about this one right here? What about this guy? Now we've got h of x is 1 divided by the quantity x minus 2 squared. What do you think is going to happen there as x approaches limit of h of x as x approaches 2 is what this time, do you think? What do you think?
Wouldn't this one be unbounded?
It is unbounded, yeah. So it doesn't exist. The answer is technically dne, but, and we'll talk more about this soon, get into more detail, we can provide a little better answer than just plain old does not exist. What do you think? Infinity, yeah. How come? Because that ant, whether he's approaching 2 from the left or the right, that ant is climbing an infinitely high hill, and so he anticipates that he's going to be stepping on a point that's infinitely high from either direction. So we actually can, even though infinity is not a number, and therefore it's not an answer, right? The limit doesn't exist because infinity is not a satisfactory answer in terms of pinning down a limit. It's, right? What does infinity mean? You can't ever get there. But that is more informative to us. It's called an infinite limit, but at least it tells us something about the behavior. It's an infinite peak from both sides. Okay? Say it again. Right, there is no point on the graph. There's no place you could ever stand. Yeah, okay. Okay. All right. Each of the three functions is undefined at x equals 2, but just making that statement doesn't tell us much. We can be much more specific than that, right? Okay. All right. So we already kind of talked about this, right? What is, by the way, we already answered the question, what's the limit as x approaches 2? You guys already told me that is 4. What's the limit as x approaches 0? 2. Are those limits any different? Is one more special than the other? No. They're equally valid limits. It's insignificant that the function doesn't actually exist at 2 because the limits don't care. You never get to C when you're taking a limit. Okay? Just quick, I mean, you can see that in this case, graphically speaking, we can see that because this point has a y-coordinate of 3, the limit is 3, even though you never get there. That's where the ant anticipates stepping. Okay? All right, so why don't you guys try this? Why don't you jump onto Desmos and try building a table of values that's going to help you determine what is the limit of this bizarre function of h as h approaches 0. Okay. Is this function defined at 0, by the way? What's the red flag? What can you look at immediately and say, nope, doesn't work? There's an h in the denominator, right? You can't divide by 0. So the function is clearly undefined at 0, but I want to know what its limit is. Take a second and try that out, then we'll talk about it. So where are you going to go? Maybe something like that. There's your function, right? We just defined the function using x's instead. It's a little easier. And then we built a table. Remember how to build the table. Hit the gear and build table from the function. You're just going to pick values bracketing 0. And you just want to get increasingly close. So maybe we start off with negative 0.01 and positive 0.01. But if you do that, that's not going to get it close enough, right? Because that's only bracketing. That means your output is somewhere between 486.6 and 339.3. That's way, who knows? That's way too big a gap. So you keep squeezing these values closer and closer together around 0 until you get to a point where you can see, if I want to round to 2 places, that means out to 3 decimal places, that digit is not changing, so I can round. That make sense? So once I know that both of these out to 3 decimal places are 403.428, and after that I don't know what's going on. That means guaranteed that's going to round to 403.43. That 8 rounds, that pushes that other digit up to a 3. See what I'm saying? You just keep adding zeros until you get enough accuracy. If I asked you to tell me out to 4 decimal places, you'd probably have to add some more zeros in there to get even closer, right? So you can approach from the left and the right until you can anticipate what value is squeezed in between. Okay? Give me thumbs on that. Does that make sense? Okay? And that's a numerical technique for evaluating a limit. Okay? Do you see any disadvantages to that? Anytime you use a numerical technique or a graphical technique, what's the inherent disadvantage? Do I ever know the exact answer? I'm always just approximating. It's just, am I getting a good enough approximation, right? So when we get to evaluating limits analytically, we're going to get exact answers, which is great. Okay, but that relies on some algebra stuff. Okay. Okay. I'll put a picture in our notes. See the deal there, Anson? You're trying to get the values to the left and the right of 0 close enough that the numbers that they're outputting don't change to a certain number of decimal places, and then you're accurate enough. Okay. Yeah. Okay. So you just have to squeeze in close enough so you hit your target. Okay. So there's 3 approaches to evaluating limits: numerical, which would mean tables; graphical approaches, which would mean graphs; and analytical approaches, which we're going to deal with soon. Probably we'll maybe hit that tomorrow, not today. Okay. So from this very brief informal look at one limit, let's start to develop an intuitive definition of a limit. So we can think of the limit as a function at a number a. We use c. This textbook uses a. I think this is out of OpenStax. I just pull stuff from various textbooks. As being the number L that the function the functional values approach as the x values approach a, provided such a real number L exists. Stated more carefully, here's what we get. So now let's look at this definition, and we're going to move from a more formal definition down to a simpler definition, more of a working definition that we can use quickly and easily in class, right? So let f of x be a function defined at all values in an open interval containing a. Okay? What's that mean? What's an open interval in math? Like if I want to look at, here's an interval, you tell me, is this interval open or closed? It's closed. How come? Because it includes brackets, so the endpoints are included, so it's a closed interval. What would I need to do to make that an open interval? Yeah, okay, so now the endpoints are not included. So think what this statement is saying then. Let's just dissect this. Let f be a function defined at all values in an open interval containing a, okay, with the possible exception of a itself. So all the x values in the neighborhood, that's literally a word we use in math, the neighborhood, in the neighborhood of a, meaning values surrounding a, if the function is defined at all those values, doesn't necessarily have to be defined at a, because we looked at some limits where of places where the functions were undefined, right? If that's true, and let L be a real number, if all values of the function f of x approach the real number L as the values of x not equaling a, right? We never get to a. As the values of x approach the number a, then we can say that the limit of f of x as x approaches a is L, okay? More succinctly, we could say as x gets closer to a, f of x gets closer and stays closer to L. That's it, okay? So our informal definition then is just this. The limit of f of x as x approaches a is L. That's how we would write it, okay? Make sense? Okay. Okay, we can estimate limits by constructing tables of values and by looking at graphs. Okay, so just real quick, just quiz yourself on this a little bit here. What is the limit? Here's my function g of x. You guys just show me, put a number up on your fingers. What's the limit of g of x as x approaches -1? Good. Yeah, it's 3. It's not 4, right? It's 3. Oh, what's it? There we go. Yep. Okay. What is, while we're at it, what is g of -1? It's 4. The value of the function does not coincide with the value of the limit here. That's okay. The limit only cares about what we think we're going to step on, right? What point the ant thinks he's going to step on. Okay? So sometimes it's helpful to expand our thinking about limits. Helpful to consider limits from either the left of a value or the right of a value. Okay? And so we would say the limit from the left, these are called one-sided limits. The limit from the left is what we get. Here's how we would write it. Okay? The limit of f of x as x approaches a with this superscript minus or negative, right? What's that saying? That's saying the limit of f of x as x approaches a from the direction of negative infinity. So from the negative, right? From the left. Read from the left. Is L. What does that mean then? In terms of an ant walking on the function, describe what that means. Go ahead, Sophia. I can already tell you're on the right track. Okay, going from left to right, an ant approaching an x value of a would anticipate stepping on a y value of L, right? Of L, okay? So then a limit from the right, what do you think that the nomenclature is going to be? Well, we just put a plus sign as our superscript. What's that tell us? The limit of f of x as x approaches a from the direction of positive infinity, meaning from the right, is L. Would just say an ant walking from right to left approaching an x value of a would anticipate stepping on a y value of L, right? Good? Okay, why is this so important? Well, because a lot of times we really only are concerned with approaching a value from one side or the other. A lot of times we don't care about from both sides. We are specifically interested in approaching from one side. But the other thing is this. Two-sided limits can now be defined in terms of one-sided limits. So now we could say something bigger. We could say the limit of f of x as x approaches a is equal to L if and only if the limit from the left is equal to L and the limit from the right is equal to L. Right? The two one-sided limits must exist and agree in order for the two-sided limit to make sense. Because remember, we already talked about an example like this. If we go back to, what example was it? It was this guy, right here, right? What did we say about that? The limit doesn't exist because ants approaching from opposite directions anticipate stepping on different places. So we said no limit. Now, in terms of one-sided limits, we know why. The limit from the left and the limit from the right, though they both exist, they don't agree.
So there's a cycle on them, so they charge at 15-minute intervals.
Oh, okay.
Turn it off, but it'll still charge them all, just one half the charge.
For a part of the time. Gotcha. Okay, and that charger's okay, you think?
Yeah.
Okay, perfect. All right. Make sense? Okay. Oops. Okay, so there it is, right? And then I kind of gave you a little, this will be in your notes. I'll publish it today. So here's kind of the formal definition. Here's how we interpret this. The one-sided limit of a function as x approaches the value a from the left corresponds to the y value the ants anticipate stepping on. Same thing for the right. Okay. Left is in red, right is in blue. And we all know that red and blue together make purple. So there's your two-sided limit in purple. How about that? Okay. And I mean, really, we kind of knocked that out. I mean, this is just now, it's just a matter of just some examples of how can we evaluate limits using tables. What do you think the value in the middle is going to be? 3. There's my limit, right? So the limit of f of x as x approaches 1 is 3, okay? Okay, how about this one? Why don't you guys try this one real quick? Just jump into Desmos and tell me, first of all, is this function defined at 0? No. Okay, but I want to know what the limit is. Turns out this is a very important function. We use this one all the time. So just use a graph and tell me what the answer is going to be. What mode would you need to be in, by the way, if you're doing trig functions and we haven't specified something different? What's the default mode you'd want to be in if you go into a calculator and you're doing trig functions? Radians mode, not degrees, right? You need to be in radians mode. In Desmos, that's over on the right. There's I think there's like a gear setting or something like that. You can see settings. Make sure you're in radians mode. In this case, you get the same answer either way, but a lot of times you won't. I want an exact answer. Oh, nope, something's wrong. Limit of sine x over x as x approaches 0. Something's wrong. What is the answer? Mm-hmm. Yep. Should be 1. Just looking at the graph, and this is pretty easy to convince yourself of this. If we there's my graph, right? Okay, let's acquaint ourselves with Desmos. Desmos is a remarkable tool. You will use Desmos a lot. When you get to college, you'll use maybe some higher-end computer algebra systems. What's the one Andy uses all the time now? It's I think they use MathLab all the time. MathLab's a big one. I think it's inexpensive and colleges use it all the time. How could I make this graph look better? I mean, I could just zoom in, but if I want to go up to the gear and like specify something here, like I want to approach 0. If I want to make this thing look a little more dramatic, I could go into the gear and I could let my x-axis go from like -1 1.1 to positive 1.1. Oh, not the x-axis. Sorry, I meant the y-axis, didn't I? Whoops. Let the y-axis go from negative 1.1 to positive 1.1. Now it looks a little better, doesn't it? Right? And you can also just zoom in and drag things. But what value is that pretty clearly approaching there? What y value? 1. Yeah, you can see that's approaching 1, isn't it? Right? So the limit is equal to 1. How about that? Okay. And you guys could use a table and do this one. They have not installed, there's some problems with it, my TI-84 emulator, so I can't really show you this stuff on the TI-84 yet, but as soon as it's installed, I'll go back and show all this stuff to you. Okay, how about this one? Discuss in terms of a one-sided limit. That's g of x. Who can tell me, like, what would I write down if I want to write down the limit from the left, the important limit from the left here? What would be the interesting one, probably? Tell me what to write. The limit, well, g of x, as x, okay, 2 from the left, so 2 negative, right, is equal to negative 1. There you go. Okay. How about the limit from the right? Two from the right, good, is, so what about, does a two-sided limit exist? Thumbs up or down? Down, does not exist, good. Okay. What's the limit? This is h of x. What's the limit of h of x as x approaches 2 from the left? Infinity. It's undefined, but we could say infinity, couldn't we? Okay, what's the limit of h of x as x approaches 2 from the right? Okay, so even though the two-sided limit doesn't exist, we can say something interesting about it, which is the limit of h of x as x approaches 2 is what? Infinity. The one-sided limits agree, so at least we can say something consistent about it. Could I do that? We're out of here in 1 minute. Okay, why don't you, we'll go ahead and close them up.